When we analyze a global supply chain, we see constant, synchronized physical motion, goods moving continuously across oceans, rail lines, and highways. The immediate assumption is that physical distance and geographic barriers are the primary hurdles to fulfilling global demand. But the true constraint governing this system is elapsed time. A single delayed component in an Asian factory or a stalled truck at a European border creates cascading mathematical failures across the entire production schedule. Precisely calculating this elapsed time allows organizations to determine exactly when to trigger reorder points and how much safety stock to hold in reserve. This calculation acts as a strict, non-negotiable input for sales and operations planning, and it directly dictates the efficiency of a company's cash-to-cash cycle. Achieving structural resilience in a supply chain requires rigorously modeling the complete replenishment timeline. In operations management, this metric is known as supply lead time. The Association for Supply Chain Management, or ASCM, provides a strict definition. Supply lead time is the total elapsed time from when a supply requirement is identified until the material is available for use at the required location. The phrase total elapsed time is deliberate. It encompasses every internal workflow and external variable. It is not confined to the external purchasing phase. The clock starts at the exact moment a supply requirement is mathematically identified by the system or an order is formally released by a planner, and the clock only stops at the moment the material is physically available for use at the required production line or destination bin. Defining the metric this way forces practitioners to measure the end-to-end operational reality, rather than isolating and measuring only the external supplier's activity. This diagram illustrates the components of supply lead time. To build an accurate model, we must deconstruct this total timeline into a 4-stage structural formula to see exactly where time accumulates. Stage 1 is administrative time. The clock is ticking while the system identifies the requirement, generates a purchase requisition, goes through internal approvals, and finally releases the purchase order. Stage 2 is supplier lead time. This covers the vendor's internal process, acknowledging the order, manufacturing or picking the items, and executing quality checks before the goods leave their dock. Stage 3 is transportation lead time. This accounts for domestic or international transit, transferring between different freight modes and navigating regulatory customs clearance. Stage 4 is receiving and internal handling. The goods have arrived, but the clock is still running during final receiving inspections and the physical movement of the goods to the storage rack or production line. Only when the forklift places the pallet in its final, usable destination does the final internal handling phase conclude. Customs bottlenecks in Stage 3 and internal put-away delays in Stage 4 are the most frequently overlooked traps. This is where invisible time accumulates in planning models. Omitting any of these 4 phases creates a systematic lag in the replenishment cycle, which often leads to material requirements planning systems triggering orders too late to meet actual demand. This stacked bar chart compares 3 distinct lead time profiles. It shows how the distribution of our 4 stages shifts radically depending on the physical context of the supply chain. In a manufacturing environment relying on an imported component, an 18-day ocean freight and customs phase dominates the 35-day total duration. Transportation is the primary variable. Contrast this with a domestic retail vendor. We see a balanced, rapid 6-day profile.
Fast internal processing, 2 days of supplier picking, and a short 2-day truck transport. Now look at an internal make-to-stock environment. Notice that production scheduling wait times consume 3 full days, a massive percentage of the 9-day total. In internal transfer scenarios, the administrative wait state, simply waiting for a machine to become available, often takes nearly as long as the physical manufacturing process itself. Total lead time duration is highly sensitive to the structural model of the specific network. Each environment requires a customized mathematical approach to manage inventory levels effectively. Confusing precise academic terminology leads to flawed systemic planning. This matrix clears up the most dangerous professional misconceptions. The primary fallacy is equating supply lead time with supplier lead time. Supplier lead time measures only the duration inside the vendor's facility. Supply lead time captures the total end-to-end replenishment wait. Next is cycle time. This is strictly defined as the duration required to complete a single process once it has been initiated.
It must never be equated with overall lead time. The second major fallacy is treating lead time as a fixed, deterministic constant in planning software. It is a variable, subject to daily external shocks like port strikes or weather events. Relying on these misunderstandings causes planning systems to severely miscalculate safety stock. Using precise apex vocabulary is mandatory for the survival of the supply network. Planners weaponize this exact total time parameter inside material requirements planning systems. The MRP uses this total duration to offset demand and trigger purchase orders exactly when needed. This logic directly controls the mathematical calculation of reorder points. Accurate lead times prevent both catastrophic stockouts and the financial drain of holding bloated inventory. Analyzing these components allows organizations to categorize their supplier network. Reliable vendors are segmented strategically, while variable vendors are managed tactically. When ocean transit times become entirely unpredictable and severely delayed, companies execute a swift physical shift to nearshoring. Total lead time data is the definitive input executives use when evaluating the cost-benefit of maintaining an offshore supplier versus transitioning to a nearshore partner. Supply lead time acts as the foundational parameter that dictates the physical design and geographic layout of the entire global network. This graph charts supply lead time variability. Recent disruptions have increased statistical variance, shifting focus from averages to managing outliers. To counteract volatility, the industry is migrating to dual sourcing and lead time compression strategies, pulling severe spikes back to a stable mean. Relying on static historical averages is no longer mathematically sufficient to manage risk in a frequently disrupted environment. Organizations are countering this uncertainty by deploying real-time tracking network visibility. Digital control towers and real-time ETA tracking are replacing static assumptions with dynamic, actionable visibility, allowing planners to reroute goods in transit. Supply lead time is a comprehensive multi-component apex metric. It captures the true end-to-end reality of replenishment, from the initial requisition to final physical put-away. The operational directive is clear. This timeline must be actively managed. Planners must monitor both its average duration and its unpredictable variance. This leaves a critical question for your own network operations. Where are you buffering uncertainty? Inventory, time, or capacity? Mastery of these networks requires calculating exactly where to buffer the system against mathematical uncertainty.